When we throw a ball upwards, it falls back on the earth. We know that this is because of the gravitational force exerted by the earth on the ball. But according to the law of gravitation, every object attracts every other object in the universe. So while the earth attracts the ball, even the ball attracts the earth. Then why don't we see the earth moving upwards towards the ball? To find out the reason, let us calculate the gravitational force exerted by the earth and the ball on each other. The gravitational force exerted by the earth and the ball on each other is given by 6.67 times 10 to the power minus 11 times mass of the ball times mass of the earth divided by r square, where r is the distance of the ball from the center of the earth. Now mass of earth is a constant and is equal to 6 into 10 to the power 24 kgs. Let us assume that the mass of the ball is 200 grams, that is 0.2 kgs. Now if we are conducting this experiment at sea level, the distance of the ball from the center of the earth would be equal to the radius of the earth plus the height of the ball from the surface of the earth. Let us assume that the ball reaches a height of 20 meters from the surface of the earth. So r would be equal to 64,000,000 meters, which is the radius of the earth, plus 20 meters. Now, given that 20 is a very insignificant value, r is approximately equal to the radius of the earth, which is 6.4 into 10 to the power 6 meters. Now, replacing the values of mb, me, and r square in F, we get F to be approximately equal to 2 newtons. That is, the earth and the ball are attracting each other with a force equal to approximately 2 newtons. Now, let us find out by how much would the earth accelerate because of this force being applied on it. We know from Newton's second law that force is equal to mass into acceleration. Here, force is equal to 2 newtons. Mass is the mass of the earth and acceleration is the acceleration of the earth. We know that the mass of the earth is 6 into 10 to the power 24 kgs. Hence, the acceleration of the earth would be equal to 2 divided by 6 into 10 to the power 24 whole meters per second square, which is equal to 0.33 into 10 to the power minus 24 meters per second square, which is approximately equal to 0. So the acceleration of the earth is approximately equal to 0. And that is why we do not see the earth moving upwards towards the ball. Now let us also find out the acceleration of the ball caused due to the gravitational pull of the earth. Again, using Newton's second law, we have force is equal to mass into acceleration. Force is approximately 2 newtons. Mass of the ball into acceleration of the ball. We had assumed that mass of the ball is 0.2 kgs. So acceleration of the ball is equal to 2 divided by 0.2, which is 10 meters per second square. Note that this is also an approximate value. Why? Because the force which we are using here, that is 2 newtons, was an approximate value. So the acceleration of the ball due to the gravitational pull of the earth is approximately 10 meters per second square. Now, if we were to take 2 balls to the tallest building on earth and we were to drop it from there, which one would reach the earth faster? Well, once we drop the ball, we know that both the balls would experience an acceleration due to the gravitational pull of the earth. So the ball which experiences a greater acceleration due to the gravitational pull of the earth would reach the ground faster. So let us calculate the acceleration of a body caused due to the gravitational pull of the earth. Well, force exerted by an earth on an object due to gravity is G times MO times ME by R square, where G is the universal gravitational constant, MO is the mass of the object, ME is the mass of the earth, and R square is the distance of the object from the center of the earth. So from Newton's second law, acceleration due to gravity would be the gravitational force of the earth divided by the mass of the object. That is, the acceleration due to gravity experienced by an object would be the gravitational force of the earth divided by the mass of the object. Now let us substitute the value of this here. So we get G times MO times ME divided by R square whole divided by MO. So here MO and MO cancels out. So we have acceleration due to gravity experienced by an object is equal to G times ME divided by R square. Observe that acceleration due to gravity experienced by an object is independent of the mass of the object. It depends on the universal gravitational constant, mass of the earth, and the distance of the object from the center of the earth. So if two objects are dropped from the same point, the acceleration due to gravity would be the same. And hence, both the balls would reach the earth at the same time. Now let us find the value of this acceleration due to gravity. Well, acceleration due to gravity is G times ME by R square. G is the universal gravitational constant and is given by 6.67 times 10 to the power minus 11 Newton meter square by kg square. Mass of the earth is also constant and it is equal to 6 into 10 to the power 24 kgs. Now R, which is the distance of the object from the center of the earth. Now the distance of the object from the center of the earth would be equal to the radius of the earth plus the distance of the object from the surface of the earth. Given that the radius of the earth is this huge number, 6,400 kilometers or 6400000 meters, the other part, which is the distance of the object from the surface of the earth, would be very small in comparison to this. And hence, we can approximate R with the radius of the earth. So substituting the values of G, ME and R into this, we can get the value of small g, which we get as approximately 9.8 meter per second square. That is, the earth attracts all objects towards its center with an acceleration of 9.8 meters per second square. That is, because of the gravitational pull of the earth, all objects experience an increase in velocity of 9.8 meter per second per second. Note that the acceleration due to gravity is a constant and is denoted by small g. Do not confuse this small g with this capital G, which is the universal gravitational constant. So all objects experience an acceleration due to the gravitational pull of the earth, and this acceleration is approximately equal to 9.8 meter per second square. Galileo was the first person to prove that time taken to reach the ground is independent of the masses of the object if they are thrown from the same height. It is said that he dropped several balls from the Leaning Tower of Pisa to observe that irrespective of the size or mass of the ball, all the balls took the same time to reach the ground. Hence, acceleration due to gravity is independent of the mass of the object. Now, if acceleration due to gravity is independent of the mass of the object, why is it that when we drop a feather and a coin, the feather takes more time to reach the ground? Well, this is because of air resistance. Just like all surfaces exert a frictional force on any object placed on them which opposes the motion of the object, air also exerts a force on any body opposing the motion of the body. So for a body falling downwards, the force is exerted in the upward direction, and for a body moving up, the force is exerted in the lower direction. So all bodies experience air resistance. So the air resistance exerted on the feather is greater than that on the coin, and hence the feather takes a longer time to reach the ground. If we were to remove air, that is, if we create a vacuum, there would be no air resistance, and then both the feather and the coin would take the same time to reach the ground.